Thank you very much, Michael. Very fascinating talk. So next we will have a 20-minute panel discussion where we will take questions from the audience. So I will call John also and Victor to the floor. So. Yep. Yeah. All three. Does anyone have some question? I will try to.
Lucky, you're the TA.
Hello. Oh, wait. Hi, yes. My name is Kyle Cahill. I recently defended my PhD in physics under Mukesh Damala at Georgia State University. As part of my dissertation, I actually developed and defended a physically grounded account of cognition as a physical system, describing the brain's energy allocation and reallocation over time, including a complete Lagrangian and Hamiltonian formalism, as well as a complete description of the theory's thermodynamic reconstruction. I used a gauge theoretic model to constrain the energy allocation in both the Lagrangian and Hamiltonian representations. I considered a Lorentz gauge to be a natural choice for the field construction. My advisor basically described the framework himself described the framework as a physically plausible extension of Carl Friston's free energy principle. And I believe it could offer a meaningful contribution to our understanding of cognition and neural function more broadly. I'm not interested in reinventing the wheel, and I would like to interface my theory with the tools and techniques already developed in neural field theory as presented here. I was curious about how you might approach this in terms of grounding it in known physiology, and how you might interface a Lorentz gauge 4 vector with neural field theory. Would you consider like the D'Alembert operator as an appropriate tool, or whether there's another approach you'd recommend? I know this is a very technical question, and you're all hearing about this for the first time, so if now is not the right moment, I'll be happy to follow up and discuss this after the session. Thank you.
Okay, thank you. Well, I am basically familiar with Carl Friston's gauge theory, but I'm not going to be able to jump in and answer your question off the cuff. So unless Victor can do it, I'm going to have a chat with you over coffee.
You want to connect? This is, yeah, good. Thank you. You want to connect to neural field platforms in order to test some of the principles that you're looking into in more physiologically based models and frameworks. Maybe also testing it against data. Yeah? What I can recommend there is there are multiple toolboxes available. One of them has been developed by the Breakspear Lab. Yeah? That is very specific for neural field theory. If you want to go larger to full brain network models, also supporting neural field theory at very high resolutions, pretty much as what I have shown towards the end, I suggest to check out the virtual brain framework. In Europe, we have a platform. Actually, it's a digital neuroscience infrastructure. In Europe, we operate a lot with infrastructures federated across many different laboratories. It's called eBrains. You saw the logo on my last slide, EBRAINS. If you add .eu, you find its website. This provides you with an entry point through many of the aspects that you are interested in. Yeah? And if you're wondering if the D'Alembert operator is a good first step into this direction, for the homogeneous equations, yes. For the heterogeneities coming from the white matter, no, because it doesn't satisfy certain symmetries. What you can do is you can, and that's what I'm doing all the time, assume weak coupling from the heterogeneities and consider this as a perturbation. Yeah? Then you can actually take this as a starting point and see how these perturbations propagate through your activity.
That's interesting because my theory utilizes that first order My theory actually utilizes the first order perturbation in its construction, so we can have a discussion about
Then
that.
you can use some perturbation theory of higher orders and test this out systematically. So these are things that can be done, yeah, and have been done, by the way, already to some degree.
So I was wondering, when you have these models with tens of thousands of vertices, does that make it more sensitive to differences in how the white matter connectome was reconstructed, or or do those still sort of balance out? Because you have like different sort of white matter DTI data tractography methods, like probabilistic versus deterministic, that can give you different results. And some modeling, kinds of dynamic modeling, like a lot of the neural mass models, actually, it does make a difference in terms of how closely then the reconstructed functional connectivity is to that from the data. So, yeah, does...
Can I start? Yeah. There are so many dimensions to your question. Are you worried about or concerned about the reconstruction of the DTI, or is it more the stability of the solutions coming from the high-dimensional model? But both matters, actually. Yeah? When you have the very high-dimensional model, through the intrinsic connections, you get a damping that allows actually the higher order oscillations. They are damped out stronger. So that's one of the reasons why in the presentation of Michael Breakspear you saw these smooth modes. Yeah? So they are typically less damped. That's one of the effects. But we have much more variability when we take these very high-dimensional connectomes. Yeah? There we are roughly at around 1 millimeter. Yeah? With 1 millimeter, we are, you talked about vertices, we're at about 200,000 vertices. Yeah? So it's, we have not tested yet what the variability is due to the reconstruction, and then what the consequences are with regard to the sensitivity of the dynamics that is being supported. We have literally not done this yet. At the moment, we have just arrived at a level where we are capable of generating activities sufficiently fast with this type of models at this resolution, and something that is also relevant, probably also for the gentleman before, inference. Inference at this high dimensionality is extremely difficult. Tricks needs to be handled, yeah, and all this is becoming available now, methodologically.
Yeah.
I'm not, your question went into multiple directions.
Oh, sorry.
You want to add something?
Yeah, I think, thanks, Vic, and thanks for your question. We did work with Andrew Zaleski and I think Sina Mansour, and they had some very highly resolved connectomic data. As you've intonated, when you get to that scale, it gets quite noisy, so you need quite a lot of post-processing. They employed probabilistic, diffusion-weighted imaging reconstruction, and then surface-based smoothing. And the connectome eigenmodes were first order extremely simple to the basic geometric eigenmodes, which to me shows that geometry constrains connectivity pretty well. I mean, they were smoothing the data in the geometrical space, which you have to do to get rid of spurious connections. So obviously they had geometry in the post-processing as well. But it did really reinforce to me that you get a long way with geometry, even with very highly resolved surface meshes and state-of-the-art connectomics. And then you need to ask your question, what are the non-explained residual connections doing? You know, they're there, so what is their role? And I think we need to have some hypotheses and some theory-driven insights into their likely role, rather than just making our models more and more and more complicated.
I second both those sets of comments. I think I'll throw another point into the mix. I mean, you're asking exactly the right question. The consistency of high-resolution tractography goes down a lot when you get into the thousands, never mind the tens of thousands. But there's another, I think, larger factor when you're thinking about the kind of process of building a connectome-based model, which is what you do with the matrix in, to sort of squish it and squash it and get it into the shape that is suitable for running simulations. So typically, there's some log scaling, maybe then there's some div by max, div by mean, take the Frobenius norm, lots of things that are done to the data, like at the matrix level, at the connectome, before you start plugging it into your simulations. And I think that probably has as much of an effect on any results you have than the variability you might have at sort of whether you get 10 streamlines here or 2 streamlines here on any given data set, in my opinion. And this is not a solved problem. There's no sort of agreed upon scaling for white matter connectivity in connectomes. It's sort of a problem that the field needs to settle on.
Yeah, there are more nuances I'd like to discuss, but they're looking around nervously here.
Thank you very much. My question mostly concerns Michael Breakspear's talk and Victor Jess's. I was wondering, I think, Victor's talk, there was a lot of evidence that sort of about the importance of approximations and where a certain sort of approach to approximating time delays or approximations for the of the spatial aspect of the model, they can cause sort of very extreme sort of differences in model behavior and stability, and you can completely switch into different regimes. So I was wondering if you have any sorts of ideas about the potential implications of the vastly more approximations that are made in sorts of a whole brain geometric sort of model that Michael sort of described. And I was wondering, because that model does seem to recapitulate a lot of sort of biologically plausible sort of aspects of neural dynamics, both temporally and spatially. So I was wondering, if you had any thoughts on that.
Well, I'll jump in first. I mean, to first order, at the meso and macroscopic scale, I mean, it seems that the brain is reasonably well damped. It has these infrequent excursions off this low-dimensional manifold, but it doesn't have a lot of erratic modal instability to first order, because the general linear model works quite well. You get the bimodal switching in the alpha rhythm, and in epilepsy, I think that's the macroscopic aperture. When you go down, and a lot of Victor's work was looking at more the mesoscopic, local field potentials, seizure generation in patches, as John called it, then these modal instabilities at higher spatial frequency, and with the little time delays and the loops that you may not put into the whole brain model, begin to come to the fore, and they explain things that a large-scale model may not explain. So our neural field model that I showed, plus with the hippocampus, captures, in my opinion, the spectrum and the low-frequency fingerprints of resting state and seizure activity. But if you're looking at LFPs, in particular, with intracranial recordings, and you're looking at higher frequency but very localized patches of behavior, that approximation won't be valid anymore. You might be able to put it into your model as some sort of first-order correction, but you're not going to model it per se. You might even go from a current-based model, which I showed, to a capacitance-based model, which is a lot of what Victor showed. So it depends the question, really, but I would start with the basic, I'd like to see a standard model, and then we play around with that and not have a completely different model for every single thing that we're doing, which I think the neural mass on connectome approach is a bit guilty of.
I'll make it short, but thank you for the question, first of all. I'll look at it a little more from the technical and potentially then also predictive perspective. When you, in a system with these time delays, when you look at the stationary solutions, meaning statistically stationary. They can still be dynamic. You can actually compute them, and then you can find eigenmodes. These will be the same eigenmodes in the delay system that Michael is finding, yeah? Because from the stationary solution perspective, the time delays don't matter because the system becomes stationary. Having said this, what do the time delays then do? They are not altering the spatial system, but they are altering the spatial-temporal dynamics and the stability of the different behaviors. Yeah? And this is where it becomes actually very interesting and very relevant. I try to show you with the re-entry. If you go into the literature, you find it as re-entry or iterative recurrent activations, or depending on where you are in the physiological literature, there are different terminologies being used. What we have shown you here is that delay-induced re-entry can actually cause some stabilization in propagation patterns. The propagation patterns are coming from the basic connectivity, but here it's actually the stability or instability in this particular case that is being generated. Yeah? And that's the reason why stimulation patterns or different types of virtual surgery are very important to be guided by the space-time structure of the connectivity, because you talked about seizure. You want to destabilize the epileptic seizure in order to stop either the tissue or the whole brain from seizing. Yeah? This is where the time delays will play a very, very important role. The actual spatial structure will not be affected, but the orchestration of the spatial temporal organization, there it matters. Yeah? Hence, this you see already in these different toy examples that I showed you. Yeah? In the simplest of all, with the time delay introduced other possible routes to go into instability. When you keep this in mind as a toy model, you can start testing the full brain network, which is much more complicated, but you can start hunting down what are the instabilities, how I can interact with them. And that's exactly what Paul Triebkorn in my lab is doing. He's trying to find new ways of exploiting the space-time structure, for instance, to stop seizures. Motivated by experiments in physiology, it works in the heart, and there is some evidence it may work in the brain. So now a phase-coupled directed stimulation paradigm in epileptic seizures once you know the connectivity. That's new. Yeah? So this is where it's becoming exciting.
Probably time for one.
Also, just very quick follow-up to Victor's point there. If you're interested in this recurrence phenomenon, I'll give a shameless plug to Davide's recent work, which has been evaluating that in these large-scale models with some interesting results.
About 3 more minutes for maybe one more question.
I think time delay is very important in the brain, but given there are lots of long-range connections and also variation of velocity, it's hard to be keep the constant for the time delay. And also it raises it could be quite challenging to do dynamic analysis for this probably a large of a variation of time delay. So in that case, I wonder, would you think if in real case, what is the variation of time delay may lead what kind of consequence in the brain? That's the first question. The second question is, currently it's could be quite challenging to determine the velocity of the brain, especially for the velocity in the white matter. So in that case, I wonder what's your opinion for these parts? Okay, thank you.
Well, thank you. Excellent question. And I'll jump in again first. But in the integral form of the neural field model, the time delay is yoked to the spatial distance. So there's a single propagation velocity, which means the further you're apart, implicitly the longer the time delay. So there's not a single time delay for the whole brain, which you will get in a lot of neural mass models. There's a yoking of the time delay to the distance through a conduction velocity. But there is a conduction velocity which can be estimated from physiological recordings, and it can be updated iteratively through model fitting. More complicated second-order effects can be accommodated. We had the time delay in the corticothalamic loop. Rich's work at the moment is a different time delay in corticohippocampal loops, or hippocampal thalamic loops. So yeah, there are multiple time delays. I think when you get into the sort of re-entry, runaway, excited dynamics that Victor is talking about, they become increasingly important. But that depends on the question that you're asking.
On delays, and specifically on neural fields, if you're really interested in that and sort of going to town on it mathematically, there's some interesting work from folks like Ingo Bojak on axonal velocity distributions within neural field equations. So that complicates things a lot, but there are, you know, propagators that you can construct that respect the gamma distributed velocity distribution of the fibers in most fiber tracts. Those aren't typically used in any of the work that you'll see represented here. They're sort of at this point a kind of mathematical exercise. But I think it's an open question how important velocity distributions are for brain dynamics in general. We usually just have one number per connection, right? But that is not actually how the brain works at the fiber level. There's definitely some kind of gamma distributed set of possibly bimodal of conduction delays for any given pair of brain regions, and that's not counting unmyelinated fibers. So there's a lot going on with delays that we just ignore at this point. There are frameworks for them, but it's unclear if they're worth it.
Maybe one very quick comment. We are at time.
Neural mass simulations, whole brain neural mass simulations have demonstrated that it's really critical. You just change the shape, do it bimodal, and all the resonances changes, the linear resonances, in a very systematic way. There's going to be something presented here about that. Look for distributed delays in the abstracts.
Okay, that's what we have time for now. Please keep your questions and perhaps find some of the speakers and people who work with them later. Let's give a huge round of applause to Victor, to John, and to Michael.